I am the global product manager in the company, responsible for the product portfolio and also coordinating the marketing and sales support activities in the company. Today, I will, immediately after giving a short introduction on the company, for those of you who are not familiar with Metrohm Autolab, very short slide on how we see electrocatalysis as application. And then I will go through the typical needs which we think that you researchers in electrocatalysis have. And specifically for hardware and software features which we offer as well. So Metrohm in general is a Swiss company which is based in Switzerland. It's quite a big company. It has more than 2,000 employees with a large distribution network in almost all countries worldwide. It manufactures a large range of instrumentations, titration, ion chromatography, spectroscopy, but also electrochemistry related instruments. The electrochemistry part is grouped as Metrohm electrochemistry, and it's is made of Metrohm Autolab, which we are here in the Netherlands. Also, we have a subsidiary in Spain called Metrohm DropSense. Some of you might be familiar, and we also have in Switzerland colleagues part of the Metrohm CVS group. So all three groups, manufacturing groups, are dealing with electrochemistry. Now, focusing on Metrohm Autolab, we are in Utrecht. We started in the mid-1980s, actually as a spin-off from the University of Utrecht. In 1999, we joined the Metrohm Group, and since then, still based in Utrecht. The size of the company, it's around 50 people. We do everything here. Basically, we develop instruments, modules, accessories, supplies. We make our own software here. We provide service support. So basically, everything which is related to the Metrohm Autolab instruments is made in the Netherlands, in Utrecht. So that was very shortly an introduction about who we are and how we think we contribute to the electrochemistry research. Now, focusing on electrocatalysis, initially, actually, to be honest, I prepared much more slides, but then I realized that I will run out of time if I will present everything what I wanted to say about how we see electrocatalysis as an application. So basically, this is the conclusion slide of that chapter, and I just want to mention here that there are two ways of for us of seeing electrocatalysis. We either see it as a standalone application field, because it's a very important application field and very focused on specific research type. But at the end, it includes it is included as I'm just trying to grab a laser pointer. It is included also as part of each application field itself. So however we look at applications, almost every application has an electrocatalysis part, electrocatalysis related research in it. So this helps us to find and to pinpoint the needs, the exact needs of the researchers, and basically what are the final goals of those researchers. So whenever we try to put application field and type of research into a matrix, and then do a combination of electrocatalysis type of research and application type of research, it helps us determining and dealing, trying to fulfill the needs of the researchers for specific segments. All right, so that's I would say it's enough about general introduction and application overview. I will go then into showing you what we think, and based on our more than 30 years of experience, what we see that are the typical needs in electrocatalysis research. And I will start with a very general, high-level overview. So basically, every researchers, we think they need these 4 things. They need versatility. They need specifications to match both standard and specific experimental requirements. The researchers, you guys need efficiency. You want to save time. You want features that will optimize workflows. You don't want to do things over and over again and have dead interval times. You guys, you need safety. Not necessarily, of course, you want physical safety, and I'm quite sure that all manufacturers are thinking about that, and there are so many regulations which, luckily, there are so many regulations which will assure you to be physically safe. But think about safety for your samples. You don't want to waste samples, and safety for your data as well. So you don't want to lose data. You don't want to measure for days, for weeks, and then realize that that your data it's lost or misplaced somewhere. And at the end, everything boils down to discovery. Your need is discovery. This is why you've chosen the path of research, because you want to discover something new. You want to do something which nobody else did to contribute to this world, to the society. So you want to pioneer exploration beyond current known limits and boundaries. So this is a very high level. Of course, you think that, yeah, it sounds everything like theory, but then how we tackle this? How do we try to fulfill all of these needs for you? So looking at the relevant hardware features for electrocatalysis, which will help you progress your research more efficiently and will give you versatility, and at the end will help you discover. There are some features which I think there are relevant, dominant for electrocatalysis, like having an analog scan. That's the only way to accurately measure interfacial processes, and electrocatalysis, it's all about interfacial processes. Having different way of connecting a cell. So basically, you don't want to lose quality of data due to the connections to the electrochemical cell. You want to have the right power, which means the right potential and the right current for your application. You don't want to have gaps in your measurements. So your measurement should be seamless and mostly relevant for very fast measurements. Whenever you have a time gap between different measurements, you are prone, you risk to lose information and even to generate errors in your measurements. For those of you who are doing impedance spectroscopy, you want a good and fast way of measuring that. And I also thought that having a dynamic interface, that's the instrument display, and the signage which the instrument will give to the user whenever he's all around the lab will help in achieving higher efficiency. To go a little bit into more details, so for the analog scan, for those of you which are not familiar with what analog scan is, basically whenever we apply a potential ramp, whenever you do a CV, you apply a potential ramp. There are two different ways of applying this. The classical way, for which absolutely all digital, all instruments these days, because all instruments are digital, they are computer controlled, the ramp is applied in the staircase way. And you can determine the interval time, you can determine the step potential. So all this staircase is up to a certain limit customizable. So you can set the parameters, but it will always stay a staircase. Then the other way, which will really make a difference on interfacial electrochemical measurements, is the analog the analog scan. And that means that in that specific scan, the potential ramp is applied in a true linear way. And just to show you that the current response on each of these cases is different, I will again not go into details here, but if anybody needs more details, we can take it offline and discuss it separately. But the current response is governed, is given by different laws, very simple physical laws. And at the end, it turns out that the measurement itself will be different. So the super classical cyclic voltammetry of voltammogram of platinum in sulfuric acid, in this case, the hydrogen adsorption desorption region, you see that with a CV linear scan, that's indeed the true way of measuring the electrochemical signal. And when we compare with the other ways, CV current integration, which is like a software solution to overcome the limitation of the staircase, and the CV staircase itself will give serious errors from this perspective. So having an analog scan, it's a must-have for electrocatalysis. Then having the right power for the application. As I said, electrocatalysis is part of basically any all main application segments, and depending on these application segments, different power requirements are needed. Having a dual compliance voltage, as we call it, so either a very high compliance voltage or with a limited maximum current, or a big compliance, high compliance voltage with actually having a high compliance voltage, sorry, with a limited current, or having high current measurements with a limited compliance voltage is the right solution for this. And you can see that in this visual here, I'm trying to see that basically for every application, having either high compliance with a limited current or high current with a limited compliance will fit the needs of the researchers. So either high compliance or high accuracy mode. I was mentioning electrochemical impedance spectroscopy. It's getting it is a very powerful technique, and it's getting more and more popular. Here, the important thing is basically the range of the frequency, because different phenomena on the electrode surface can be observed, can be detected at different frequency range, at different frequencies, and also the maximum and the minimum, measurable impedance. So having a wide, complete contour plot, it's also very important for you to fulfill the versatility part. I was mentioning the way to connect to your cells. So having immediately available different connectors, which will actually, you don't need to use adapters, but the cables themselves will connect already directly to the instrument. You see that the main cables are fixed to the instrument, which will make the loss of signals due to bad cable connections basically non-existent. And then the end part, which connects to the cell, is very flexible, and you can use it depending on the type of the cell which you have. Now, this the next feature which I want to mention is the so-called seamlessness, which is basically not having, when the measurement is seamless, it means that we do not have any gaps in the measurement itself between two measurement commands. And I'm showing here what could happen for a non-seamless, whenever we have a non-seamless measurement. So basically it can lead to false conclusion. You see, in theory, it's just an example. We have different responses for different phenomena which takes place. So we can have diffusion control, kinetic control, or mixed control. And if we are not able to get the data immediately after the potential step, so if we have like a gap, as I'm showing here, depending on the size of the gap, basically a false conclusion is taken from the measurement. And also, just very fast, another consequence of having a time gap, so basically not having a seamless measurement, is that basically you miscalculate, for example, a charge which you have as a result of the potential step. So because this part here, which I'm showing with my laser pointer, is undefined, and if it's not sampled, or if the potential control in this part is not accurate, then basically the errors in the calculations will appear. So having a seamless measurement for fast, specifically for fast measurements, is also crucial. The dynamic interface, even though it seems like a fancy stuff, but just think about multitasking, being able to do something else in the lab. You guys, which you have hands-on research experience, you always do something else in the lab, like polishing an electrode, cleaning, preparing another cell. It's always nice to be able to have a peek to the instrument and see the state of the measurement, the state of the instrument, the state of the experiment. Safety, data, and sample protection. I already mentioned that, but it's nice to have automatic data saving, onboard memory, so the data is saved on the board of the instrument itself. So if something unexpected is happening with the connection itself, then the data stays and can be retrieved from the instrument. Oscillation protection, and also external cell button. There are also other things, but I will just go a little bit faster. To also the design, even though it seems that it's not relevant, but an optimal shape and a small footprint is also important for the way the instrument is placed in the lab and the place you find in your busy benches, experimental benches. Now, some issues relevant to software. Of course, ease of use is one of the most important ones. Collaboration. You want to collaborate. You want to be safe. For example, also for efficiency, plotting, data management, different type of workflows, and so on. And I will show you just some examples in the way we thought that we do it, and we think it will help you in your way of working. So, for example, we created for everybody, depending on the way they work, we have an exploratory workflow. Whenever you can do your own procedure, use your own commands, build, customize whatever you want. But we also have a routine workflow where we highlight only the main parameters and you can run the same procedure over and over again. Ease of use. It's all about having everything intuitive, consistent, with drag and drop. You see, this is what I mentioned with creating your own procedure. You just drag, drop commands. They are labeled, they are very intuitive, nothing much to read about those. You can build your plots again, consistency, it's everything is drag and drop. You can also just overlay plots, again, just drag them on top of each other and basically you create your procedure very easily and you're ready to start it. In terms of integrated help, so we don't send you always read the user manual because that's an additional effort and an additional way to go. The help is integrated. You say for each command, again, consistent, there is the additional information about the command itself integrated. Also, whenever we set up, for example, a CV, we have interactive way of showing the waveform, which is basically applied. You see, it's changes in real time depending on the values which you select, so that this will also make your life easier to be able to select and to define the waveform you actually want. Plotting, also with plotting, it's basically automatic changing the colors is one of the basic nice things which everybody wants. So whenever a measurement is starting and you measure more CVs one after the other, you don't want to click afterwards and change the colors. So we immediately to save time for you, to make everything more efficient, we just change the colors automatically for you. And then if we drag and drop the plots on each other, we make it again very easily, conveniently possible, and the colors will change again automatically. Yeah.
Are you able to wrap it up? Then we also have some time for questions and
I have three more slides and that's it. So with the collaboration, we have individual usernames. Individual users can log in and then they can collaborate. They can share data files with a shared folder. We have shared library. We have personal libraries. We can export individual measurements. And I will just go to the last one. Also for efficiency, we made it possible that you can take away your computer for long measurements. We made it possible that we start the measurement it's running, it's starting with a computer, and then you can untether, disconnect your computer and use it for something else. And whenever the disconnection takes place, then you are notified how long basically you have until you have to reconnect your computer. And that was actually it. Actually, I realized that I used some of the time from my Q&A part. I'm for 4 minutes over the time. Instead of conclusions, I will just list again the things, the needs which we think that you all are looking forward to fulfill, which ends basically with being able to discover new things. And with this one, I thank you all for listening. If we still have time for questions, we can do it now. I am available to be contacted anytime by anybody, also by email. So thank you for.
So first of all, Iosif, thank you for this nice overview and this nice presentation. It looks like you are doing a lot to help this community or help material pioneers forward in the research. What I would suggest as a test to see if we can do spoken questions. So if you have a question, then please go to the top of your menu and then you are able to raise your hand. And then if I see your hand being raised, I can give you the mic or ask you to unmute and ask the question in live. So if you have a question, raise your hand. If
Also,
raising your hand is difficult, you can also just unmute. I will start with the first question. So is it correct that the analytical data from the experiment is stored locally on the device?
there are, yes. So
next to that, you have the capability in this soft or this cloud solution to share the data coming from the device with other people in a shared library or.
Yeah, so that there are two different things here. So yes, there are an integrated onboard memory. There is an integrated onboard memory on the instrument, which is it has basically two different roles. One it's for enabling untethering. So whenever you want just to remove your computer, walk away, and the instrument will keep measuring. So you can use your computer in your office. And the other role is safety. So if something unexpected happens with the Ethernet connection, or I don't know, maybe somebody just unplugs a cable, or maybe you have a crash, then still the data is retrievable from the onboard memory.
Yeah.
And the other thing which you mentioned was sharing with cloud. At this point, we still do not have the application to go to cloud. It is in our architecture, but it will take a little bit of time to implement it.
Yeah.
But sharing basically is between different users, as I showed, I think, in this screen. Different users can log in, can access Intello, the software, and then if somebody saves in the shared library, then all the users will see the same thing. So you don't have to email the data to each other or so on. And also you can keep it in an ordered way.
But you mean all the users that are using this type of software?
Exactly.
All the users within one research university or within one company?
For now, as we speak, it's all users on one computer, on one system. But as I said, the architecture allows us to expand this also in the network, in the cloud. It will take a little bit of time for us to implement it, but we are aware of that, and it will come in the future.
Is that also something that you really see as important? I think in the European Union, there is this movement Plan S to also share more of the raw data from the experiments. So in scientific publications, we only share, let's say, the final results or this very nice graph that we concluded out of the data. But most of the raw data is then not shared or lost. Do you see an important role for Metrohm also to facilitate that part via this cloud that you are at least working on? Or
if we will see the trend picking up, then absolutely we are ready to do it. We have to hear from you guys. If you think that this will be needed, then absolutely. So that's why we need to stay in close touch with our users, and we are doing our best to do that.
This is, by the way, also something that from VS Particle side we are thinking on. We already have this cloud connection. One moment. Yes, we already have this cloud connection for our tools. So if people use a certain recipe on our systems to synthesize a specific nanoparticle, then maybe we should also think about how we can connect that, let's say, recipe data to your analytical data, so that you have the full package, that you know this material has been synthesized in this way with this, let's say, software, and then this was the measurement that I did.
Yeah, to create like common databases to give access to the same place, and then people can store information related to the same topic altogether.
Yeah,
that's it might be that it will pick up, and this will be the trend for the next few years.
Yeah, great to see that.
All right.
Also,
so for those of you who ever need any demonstration, any other details, just feel free to contact us and we will take care of it. Thank you again.